Hello, everybody. So I assigned this to you guys like eons ago, but I kind of want to address it with you because I never did it formally. So we're talking about operations on functions. Like we can add two functions, we can subtract them, we can multiply them, we can divide them, and then we can even do something called composing them, which we will get into at some point. But anyway, it's just a matter of notation that if you see something like f plus g of x, it's the same thing as doing f of x plus g of x. F of x minus g of x is the same thing as f minus g of x. This is how this reads. This is f times g of x, and this would be f of x times g of x. And if you notice on number 4, which I find super interesting, the quotient of f and g, it's f of x divided by g of x, where g of x cannot equal 0. So, all of a sudden, when we do a quotient, we now automatically have a domain restriction, whereas on the other 3, we really didn't, because adding, subtracting, and multiplying aren't really going to do much. So, and you can do things, and if you notice that the difference of g of x minus f of x will not always equal f of x minus g of x because of that negative sign. Remember, that completely matters. And then also, if you do the quotient of g of x over f of x is now the one who's going to have restrictions. So those are good things to keep in mind. So in these problems, and I'll go through some of these with you, you're actually given two functions. You're given f of x, which is a linear function, and you're given g of x, which is a quadratic function. Now, I would strongly encourage you to actually sketch these functions like f of x plus g of x and f of x minus g of x, all of these on Desmos, just to kind of get an idea of what they are suddenly going to look like. Because when I look at this, I'm taking a linear function and I'm adding it to a quadratic function. I can assure you it's still going to be a quadratic function, but some things are going to change as far as that goes. So it's still going to be a quadratic function that opens up because it's going to be 2x minus 3 plus x squared minus 1. So if I combine all of my like terms, I have x squared plus 2x minus 4. So that is going to be, again, another parabola that happens to open up. Now what's interesting, though, is that if I subtract them, I'm going to have 2x minus 3 minus, and you know damn well I'm going to tell you to throw parentheses in there, of x squared minus 1. So now when you distribute the negative sign through, minus x squared plus 1, you wind up with negative x squared plus 2x plus 2. So now by subtracting that quadratic function, you still have a quadratic function, but instead of opening down, it's actually going to open up. And if I'm you, like I said, I would go ahead and sketch these on Desmos or sketch them in your graphing calculators to actually see what they look like, okay? You can also multiply these two functions, and what's interesting, and I hope you guys realize this, that if I do 2x minus 3 times an x squared minus 1, can you predict, this thing is open, I gotta close that, can you predict what the highest degree is gonna be? Think about it, you're taking a linear function and you're multiplying it by a quadratic function. If you said cubic function, I'm quite proud. So that means we could do 2x cubed minus 2x minus 3x squared plus 3. And I like to do the terms in order, so it should be 2x cubed minus 3x squared minus 2x plus 3. So when I multiply a linear function and a quadratic function, I wind up with a cubic function. Now, over here what's interesting is I'm doing f of x divided by g of x. So I have 2x minus 3 divided by x squared minus 1. If you guys can identify what kind of a function that is, I'd be super proud. And if you said it is rational, I'm going to say bravo to you. Now, we know it's going to have a domain restriction, right? It's definitely going to have a domain restriction. Slide this over a little bit. A little domain restriction. So if I asked you what it was, what would you tell me? I hope you said x cannot equal 1, but it also can equal negative 1. Because if you look at this, this represents the difference of two squares, so it's x plus 1 times x minus 1. And again, the restrictions on your domain are the values that cause the denominator to equal 0. So 1 is going to work, but so is negative 1, because if I square negative 1, I make it a positive, so I'm still going to wind up with 1 minus 1 for both. And if I actually do a factored form of this difference of two squares, and I solve both of these, set them both equal to 0 and solve for x, I'll get negative 1 for this guy and positive 1 for that guy. So it's already telling you that you have two restrictions on your domain. Now, this is a rational function. Typically, when we have restrictions on our domains, that automatically means from a graphical perspective, we have, you guessed it, two vertical asymptotes. So this is going to be two vertical asymptotes, one here at +1 and one there at -1. So when you go to graph this, just to get a quick idea, again, I would go on to Desmos to see what this thing looks like, but I know that I have something going on here at -1 and at +1, -1 and x equals 1. And then the other thing is that if I look at this, and as x gets bigger and bigger, the squared outdoes the x, so therefore this whole ratio is going to 0. So now I know that my range is going to be y can't equal 0, so I have a horizontal asymptote, so y cannot equal 0. So there are only these restrictions on here. So what that means is that there's something going on there's like almost 6 quadrants now, if you can look at that, right? And we'll revisit that when we actually study full-blown families of rational functions. But your graph is going to be up here or down here. Something interesting happens in the middle, and then it's either going to be up there or down there. Again, go see Desmos and see what it does, okay? Yeah, so, or, hold on. Let's go and we'll do on my calculator, because I just changed the batteries on this thing. So I'm very excited. So 2x minus 3. I strongly encourage you guys to do it too. And don't forget, put everybody in parentheses, x squared minus 1. And I'm going to do a zoom 6 for a standard window. So if you look at this graph, right, if you look at this graph, you can clearly see strange things are happening where, you know, it's those two asymptotes that I talked about where there's an asymptote going straight down here and then straight down there. And then you have these weird curves going here and a weird curve going over there. Stop. So then that just goes to show you how very cool and interesting that this graph looks for this particular rational function. And we will find out why these look the way that they do, okay? Now, what I might want to do actually, just to see it even better, is I'm going to change my window for x min and x maximum to 5 and -5 so we can get a better feel for what that looks like, okay? Now, I want to show you something. It looks interesting because if you look at this guy right over here, this one, it actually looks like it crosses over that horizontal asymptote, doesn't it? Because it does. Newsflash. The only asymptotes that a function will ever cross, if it ever does, is a horizontal asymptote. It will never cross a vertical asymptote. Just an FYI. Just some cool things. So, but what I want to point out, though, is going back, is that we took a linear function and we divided it by a quadratic function, and this is the crazy thing we got out of there, was this guy right over here. So what's really cool is when you do operations on functions, and I'm going to say specifically the quotients, this is some of the cuckoo-doodle stuff that actually comes out of it. Now, getting over here, if it's asking you to find f plus g of 3, it's asking you to do f of 3 plus g of 3. So up here, we know what f of 3 is. We can find f of 3, and over here we can find out what g of 3 is. So f of 3 is 6 minus 3, which is 3, plus, and then 3 squared is 9 minus 1 is 8, so therefore the sum of these two is going to be 11. So if I add the two y coordinates from each one of those two functions, that's what I'm going to get. And then this one over here is saying, well, let's do f of -2 minus g of -2. So again, if I plug -2 in here, I get a -7 minus, and then g of -2 is 3, so this is going to be -10. So the difference of those two is going to wind up being -3. It's just getting comfortable with knowing that we can multiply, so divide, add, or subtract functions. And again, like I said, the interesting things happen actually is when, specifically when you multiply and especially when you divide, some crazy looking functions are born from there. Okay? Now, this guy came up over here. This was another interesting thing that I think I would like to share with you. Yes, this is Mr. Yule. Mr. Yule, did you know he's the one who taught Algebra 2 honors for probably 15 years? Yeah, so because he and I have been teaching for 17 years together here. I don't know why my printer's acting crazy. You hear that in the background? It's a little creepy sometimes. But anyway, we're given f and g. So in other words, f, the function, only represents this set of ordered pairs, and g represents this set of ordered pairs. I don't know what the functions are. In other words, the only thing that makes up these functions are these specific ordered pairs and nothing else. So when we say f of 0 plus g of 0, so if I do f of 0 plus g of 0, over here f of 0 is equal to 5. And I go down here and I look for g of 0, and that's equal to 4. So therefore, this should be equal to 9. On this one over here, it's saying find out what f of 0 is and multiply it by g of 0. So f of 0 is 5. and g of 0 is 4, so that product is going to be 20. So if I multiply those two out, I'm going to have that. If I do g of 3 minus f of 3, so g of 3 is negative 3, and then f of 3 is negative 2. So double negatives, you better automatically make those positive, my friends, okay? And that is automatically going to give you a negative 1. If I do g of 3 divided by f of 3, g of 3 is negative 3, and f of 3 is negative 2. So the sum of those, so the quotient of those is just going to give us the 3/2. You're getting the general idea, I guess, okay? Now, what's interesting over here is if I do f of negative 2 over g of negative 2, f of negative 2 is negative 1, but g of negative 2 is 0, so I sincerely hope you put undefined, okay? So that quotient does not exist. We cannot have that. When they ask you for the domain of f, it's asking you to list all of the x values in the domain, and we like to use those brackets. So it would be negative 3, comma, negative 2, comma, 0, comma, 3, comma, 5. That represents the domain. The domain of g, again, you're just choosing your x values, so that 0, 3, 5, and 7. Now, if they wanted to do the sum of f of x plus g of x, yes? The sum of f of x plus g of x would be the sum of all of those x values in the domain for both of them. So we would take into account what's overlapping and what's not. So in other words, if I were to take the first one, it would be a negative 3. They both have a negative 2, so I don't have to write that twice. There's a negative 1. There's a 0. I only have to write that once. There's a 3, a 5, and a 7. So in other words, when I say f of x plus g of x, it's like put all of those x values that they have together, and then anything that overlaps, I don't need to count it twice, okay? So if it asks you to list the ordered pairs of f of x plus g of x, find the range of f of x plus g of x. Okay? So buttons. I'll be right back. And we will continue this on the other side. Hold on a second. I want to get back over here. So I'm actually going to skip these for now in the front, and I'm going to ask you guys to tell me what you think the answers are going to be for those. And then we'll kind of take it from there. But I'm just going to go to the back of the sheet now. And it's asking you to state the domain for f of x for the first one. So if you look at this right over here, it is a square root function. And in square root functions, you guys should recognize that you can't have anything that's negative inside the square root. So we take the inside, and we make it greater than or equal to 0. And then if we subtract 4 from both sides, x has to be greater than or equal to 4, and hence the domain of this function is x is greater than or equal to negative 4. If you want to state the domain of g of x is a linear function, and you should all recognize that that is a set of all real numbers. Now, if you combine the two, it's going to be x plus 4 plus x minus 3. And that's the sum of those two. The interesting thing is that this guy still has that same domain restriction as it did before. Excuse me, so therefore the domain is still going to be x is greater than or equal to negative 4, because no matter what, I have to be negative 4 or bigger in here, which is going to naturally put a restriction on this guy over here. And then finally over here, we're going to do f of x plus 4 divided by g of x, which is x minus 3. And if you look at this, we already know the domain restriction for this guy is x has to be greater than or equal to negative 4. However, we now have a new person at the party who can't come to the party, and that is right over here is 3. So in other words, my domain is going to be x is greater than or equal to negative 4, where x cannot equal 3. So everything that's negative 4 and bigger, but anytime it tries to pass through by 3, it's not going to happen. Again, I would sketch this on Desmos, or I would sketch this on my calculator, just to see what this thing looked like. So if I were to do that, which I'm going to do right now, square root of x plus 4, close that out, divided by parentheses, always use parentheses, x minus 3. And again, I'm going to do my little zoom 6, and I hope you guys are doing it too. Okay, so as you can see, again, we got one of those little wacky kind of functions because we already knew that 3 was not going to be allowed in the domain, and you can actually see if I were to draw a vertical asymptote, it would pass through x equals 3 right there. Interesting. And then for G is asking you to state the domain of g of x over x of x, f of x, so x minus 3 over the square root of x plus 4. So we have that, which is a really interesting thing. We know that the denominator cannot equal what? The denominator cannot equal 0. But all along the way here, if I put -4 in here, my domain restriction was everything greater than or equal to -4, because if I were to plug -4 into the function, I would have the square root of 0, which is 0, which is okay. That exists. That's wonderful. But if I put -4 in here, I would have something over 0, which would be undefined, which means the domain for this function should be x is greater than -4, because it can't include -4, because -4 is going to cause your denominator to equal 0. Isn't that interesting? Isn't that interesting? And then I want you guys to answer these 2 questions for me as well. Oops. So again, I'm asking you guys to go back and see if you can go ahead and make sense of what you're seeing on these, and if you're still confused, we'll go over it as a class, okay?